Imagine a planet so extreme that instead of gentle rain, molten metal falls violently from the sky, turning its landscape into a glowing river of fire and iron. This alien world exists far beyond our solar system, where unimaginable heat and furious winds shape a planet no human could survive on. Scientists have discovered WASP-76b, a planet where iron clouds vaporize under scorching heat, only to fall as molten rain across its dark side. Winds roar across this planet at unimaginable speeds, carrying liquid metal sideways, creating metallic storms brighter than any lightning on Earth. Temperatures on WASP-76b are so extreme that metals vaporize in the atmosphere, forming clouds of iron and magnesium before condensing into rain. Picture molten iron streaking across a glowing horizon, carving rivers into the rocky surface under constant bombardment from its sun. Telescopes detect this alien phenomenon by analyzing the spectral fingerprints of metals in the planet's atmosphere from millions of kilometers away. The planet's extreme heat drives a violent cycle of vaporization, condensation, and precipitation, creating storms unlike anything ever witnessed in our solar system. Unlike Earth, where rain nourishes life, here metallic precipitation transforms the surface violently, reshaping terrain with every drop of molten iron. Observing WASP-76b remotely, scientists note rivers of glowing molten metal, carving strange channels across its ever-changing, hostile landscape. The night side of the planet allows molten metals to condense after being vaporized on the scorching day side, creating perpetual iron rainfall. This continuous cycle forms a metallic hydrological system driven entirely by heat, gravity, and extreme winds rather than water. Molten iron clouds collide mid-air as they fall, forming chaotic streams that streak across the sky like fiery ribbons. The violent storms are intensified by winds reaching thousands of kilometers per hour, forcing the molten metal to move sideways before hitting the surface. Spectroscopy reveals the presence of iron, magnesium, and other heavy elements, confirming that the rain is not water, but pure molten metal. The surface constantly changes as falling molten iron reshapes the rocky terrain, forming jagged, reflective structures that glow under its blazing sun. WASP-76b is tidally locked, meaning one side is permanently exposed to the star, while the opposite side remains in darkness, creating massive temperature gradients. Extreme heat on the day side vaporizes metals, which then travel with violent winds to condense and fall as molten rain on the night side. The planet's storms are so intense that they resemble rivers of fire streaking across an alien sky in perpetual motion. Iron rain reacts with the rocky surface, forming exotic chemical compounds and altering the planet's surface in ways impossible on Earth. Scientists use supercomputers to simulate the violent winds and molten metal dynamics, allowing predictions of storm behavior in this unthinkable environment. The planet's magnetic field may also interact with charged molten droplets, producing electromagnetic effects during the metallic storms. Each droplet of molten metal represents a dynamic interplay of heat, gravity, and atmospheric turbulence in an environment far beyond earthly extremes. Studying WASP-76b teaches us about planetary evolution, weather systems, and extreme chemical processes in alien atmospheres. Its unrelenting heat, metallic rain, and ferocious winds make this planet one of the most hostile environments ever discovered. Iron precipitation is not random. It follows patterns dictated by temperature, gravity, and atmospheric pressure, creating structured yet chaotic storms. The planet's jagged metallic landscapes are formed by constant bombardment, creating reflective surfaces that glow under extreme stellar radiation. Observation relies on remote sensing and spectroscopy, since no spacecraft could survive the molten metal rain or extreme temperatures. The violent rain cycles demonstrate that planetary weather can exist in forms beyond water-based systems, expanding our understanding of exoplanetary science. Ultra-hot Jupiters like WASP-76b reveal how close proximity to a star produces extreme atmospheric conditions and alien weather patterns. Winds carry iron droplets sideways, not vertically, creating surreal diagonal rain patterns unlike anything observed on Earth. The contrast between the scorching day side and cooler night side drives constant turbulence, shaping the planet's molten storms. Molten rain interacts with other metals and compounds, producing chemical reactions observable even from millions of kilometers away. The ongoing cycle of vaporization and precipitation forms a self-sustaining system powered entirely by stellar heat and planetary dynamics. Spectroscopy allows astronomers to detect metallic clouds, precipitation patterns, and wind speeds. The molten metal rain on WASP-76b is caused by extreme stellar heat, vaporizing iron and other metals in its atmosphere relentlessly. Daytime temperatures exceed thousands of degrees Celsius, hot enough to turn metals into a gaseous state before condensation occurs. As the vaporized iron is carried by powerful winds toward the cooler night side, it condenses into droplets of molten metal. The process is similar to water cycling on Earth, but instead of water, it involves molten iron and metals like magnesium. Tidally locked rotation ensures one side is permanently heated, while the other side provides just enough cooling for condensation to occur. The massive temperature difference between day and night drives violent winds, reaching thousands of kilometers per hour across the planet's atmosphere. These winds carry the molten metal droplets sideways rather than straight down, creating diagonal, chaotic rain streaks across the sky. The metallic rain forms under intense pressure and gravity, falling at extremely high speeds that would destroy anything it touches. Scientists model these extreme storms using supercomputers to predict how molten iron moves in such hostile conditions. Atmospheric spectroscopy allows researchers to detect iron vapor, magnesium, and other metals remotely by analyzing absorption lines in the planet's light spectrum. The interaction between vaporized metals and planetary winds is a complex process, combining heat transfer, fluid dynamics, and gravity-driven precipitation. Molten metal rain demonstrates how extreme stellar proximity and tidal locking can create alien weather systems unlike anything on Earth. On the night side, cooling temperatures allow the iron vapor to condense into tiny droplets before they fall as molten precipitation. These droplets may collide with other particles mid-air, growing larger and forming glowing streams of metallic rain. The continuous cycle of vaporization, transport, and condensation creates a self-perpetuating system of extreme weather unique to WASP-76b. Scientists refer to this as a metallic hydrological cycle, driven entirely by heat and planetary dynamics rather than water. Winds carry the molten iron horizontally, making the rain appear almost slanted due to the planet's rapid atmospheric motion. The planet's gravity ensures the molten iron falls with tremendous force, impacting the surface violently and reshaping terrain. The interaction between metal droplets and surface rocks may produce exotic chemical compounds under such extreme conditions. Heat maps of the planet show glowing iron vapor on the day side and streaks of cooling droplets on the night side. The intensity of the metallic storms is influenced by atmospheric density, wind speed, and the chemical composition of the air. Iron and magnesium clouds form high in the atmosphere, rising and falling with the thermal currents generated by extreme stellar heat. These clouds are thin, yet sufficient to create visible spectral signatures detectable with high-precision telescopes on Earth. By observing the spectral lines, scientists can confirm not only the presence of metals, but also infer wind speeds and temperature differences. The temperature difference between day and night may exceed thousands of degrees, creating dynamic flows and constant atmospheric turbulence. Researchers use computer models to simulate the evaporation, transport, and condensation processes to predict storm intensity and rainfall patterns. Molten metal rain also reflects light differently, creating a glowing, almost neon-like effect across the night side of the planet. These reflective properties may affect measurements and provide insights into the planet's atmospheric chemistry. The precipitation of molten metal illustrates extreme weather physics in conditions far beyond Earth's standards. WASP-76b serves as a natural laboratory to study heat-driven weather systems and metal condensation cycles in exoplanets. Understanding how metals behave under extreme heat and gravity can inform studies of other ultra-hot Jupiter planets. The interaction of iron droplets with other atmospheric compounds can create rare chemical reactions observable from millions of kilometers away. The metallic precipitation reshapes the planet's landscape over time, forming jagged, reflective surfaces that constantly evolve. These surface changes reveal how planetary weather can directly sculpt geological features under extreme conditions. Molten metal rain is a phenomenon driven by physics, chemistry, and planetary dynamics combined into a uniquely alien system. Studying these processes helps scientists understand atmospheric behavior under extreme conditions, potentially applicable to other distant exoplanets. The continuous iron cycle between vaporization and condensation creates a violent yet structured pattern of storms. The planet's night side acts as a cooling zone, ensuring condensation continues. Studying a planet where molten metal reigns continuously challenges our understanding of weather, chemistry, and planetary physics, revealing environments that defy all Earth-bound expectations and logic. WASP-76b's extreme storms provide insights into how intense heat, gravity, and atmospheric pressure can create a cycle entirely unlike the familiar water cycle on Earth. The continuous vaporization and precipitation of iron demonstrates a fully self-sustaining metallic weather system shaped by stellar proximity and tidal locking. Scientists wonder how molten metals interact with other compounds in the atmosphere, potentially forming strange, exotic chemical reactions observable across light years. Each iron droplet contributes to the planet's constantly shifting surface, carving jagged channels and reflective formations impossible to find on any earthly landscape. The violent interplay of wind, heat, and molten metal demonstrates how alien weather can reshape entire planetary surfaces in dramatic, unpredictable ways. Understanding WASP-76b helps scientists develop models for ultra-hot Jupiter planets, which orbit extremely close to their stars and experience intense stellar radiation. These models also aid in predicting atmospheric dynamics, storm formation, and chemical cycles on distant exoplanets with extreme conditions. Studying molten metal precipitation shows how exoplanetary atmospheres behave under temperatures that exceed thousands of degrees, providing a glimpse into extreme chemistry. The iron rain's trajectory is influenced by wind shear, gravity, and temperature gradients, creating diagonal streaks of glowing molten metal across the night side. These violent storms continuously erode and reshape the planet's terrain, forming jagged, reflective landscapes that reflect both the planet's heat and its molten rain. Spectroscopic studies allow astronomers to determine not only chemical composition, but also wind speed, temperature variations, and storm intensity in real time. Observing WASP-76b helps refine our understanding of how extreme stellar proximity drives atmospheric circulation and violent weather phenomena on alien worlds. Researchers also explore how magnetic fields may interact with molten iron, producing electrical currents and electromagnetic effects during metallic precipitation. Simulations suggest that partially ionized iron droplets could influence atmospheric conductivity, creating unpredictable but fascinating electrical phenomena in these storms. By studying ultra-hot Jupiters, scientists test the limits of planetary physics, revealing interactions between heat, gravity, and metallic precipitation unlike any earthly experience. Each storm reshapes the landscape, depositing iron in reflective layers while creating channels that flow like molten rivers, permanently altering the planet's surface. The violent weather also allows scientists to study how metals behave under extreme heat, pressure, and velocity, expanding knowledge of planetary chemistry. Iron vapor, transported by winds to the night side, condenses into molten droplets, falling at tremendous speed and reshaping everything they strike. WASP-76b's dynamic storms provide a natural laboratory for understanding condensation, transport, and precipitation processes in exotic planetary atmospheres. The extreme cycle of metal vaporization and precipitation illustrates how alien planets can form self-sustaining, complex systems without water. These violent storms remind us that planetary diversity extends far beyond Earth-like conditions, offering extreme examples of nature's creativity. The study of metallic precipitation also improves our understanding of ultra-hot Jupiter formation, their chemical composition, and their interaction with stellar radiation. Iron rain transforms the night side into glowing streams, creating a landscape constantly altered by molten flows and violent impact events. Observing these extreme processes helps refine predictions about atmospheric circulation, wind patterns, and storm frequency on other exoplanets. Continuous metallic precipitation highlights the interplay of physics and chemistry, revealing how extreme conditions produce unexpected and fascinating phenomena. These alien storms challenge our perception of weather, showing that intense heat and stellar influence can create dynamic yet structured chaos. By comparing WASP-76b with other ultra-hot Jupiters, scientists uncover patterns in wind distribution, metal condensation, and storm formation across similar exoplanets. Each droplet falling from the sky represents a perfect balance of heat, gravity, and atmospheric turbulence, forming a spectacular metallic spectacle. Studying these processes also provides insights into planetary evolution and how extreme environments shape surfaces over millions of years. The violent metallic precipitation serves as a vivid example of how physics behaves under conditions vast. Studying a planet where molten metal reigns endlessly helps scientists understand atmospheric dynamics, chemical cycles, and weather patterns in environments far beyond anything found on Earth. WASP-76b serves as a natural laboratory for exploring how extreme stellar radiation and tidal locking produce chaotic yet structured metallic storms. Observing the planet reveals how metals vaporize, travel across turbulent winds, and condense into molten droplets, forming self-perpetuating storms that continually reshape its surface. These observations refine models of exoplanetary atmospheres, helping researchers predict storm intensity, wind patterns, and precipitation behavior in ultra-hot Jupiter-type worlds. Each iron droplet demonstrates how heat, gravity, and chemical interactions create dynamic, high-energy environments unlike any terrestrial weather system. Understanding these processes expands our knowledge of planetary evolution, showing how extreme environments can sculpt landscapes over millions of years. The continuous metallic rain highlights the power of stellar radiation to drive complex atmospheric phenomena and extreme weather cycles on alien worlds. By analyzing spectral data, astronomers identify chemical compositions, temperature gradients, and wind velocities, revealing the planet's unique, violent meteorological system. WASP-76b illustrates the incredible diversity of exoplanets, emphasizing how conditions differ dramatically from our solar system's planets. These insights help refine techniques for detecting and characterizing other extreme exoplanets across the galaxy. The planet's jagged, reflective surfaces form from molten metal impacts, demonstrating how alien weather directly reshapes landscapes over time. Studying ultra-hot Jupiters like WASP-76b informs scientists about the limits of planetary physics, chemistry, and atmospheric circulation under extreme conditions. Iron rain interacts with atmospheric particles, creating chemical reactions that illuminate the planet's composition and environmental processes. Observations also reveal how heat transfer and wind currents influence droplet trajectories, resulting in diagonal, glowing streaks across the night side. Molten metal precipitation provides a dramatic illustration of energy transfer in extreme planetary atmospheres, combining chemistry, fluid dynamics, and thermodynamics. The violent storms of WASP-76b also serve as benchmarks for understanding energy distribution, temperature extremes, and chemical cycles in alien worlds. Scientists simulate these processes using supercomputers, modeling how metals vaporize, travel, and condense under extreme heat and powerful winds. The insights gained from such simulations enhance our ability to predict atmospheric behavior on other ultra-hot exoplanets. Observing WASP-76b also allows researchers to compare its storms with less extreme planets, revealing the spectrum of planetary weather diversity. These studies deepen our understanding of how planetary rotation, tidal locking, and stellar proximity shape atmospheric dynamics. Iron rain acts as both a destructive and transformative force, continuously carving the landscape while forming glowing, reflective surfaces. These observations also highlight the importance of spectroscopy in detecting chemical compositions, metallic clouds, and storm patterns remotely from Earth. Understanding metallic precipitation improves predictions of other exoplanets' atmospheres, providing clues about extreme chemistry and potential surface processes. The constant cycle of vaporization, transport, and condensation represents an alien hydrological system, unlike Earth's familiar water-based cycles. WASP-76b demonstrates that extreme weather can form naturally without water, relying entirely on metal vapor and condensation for precipitation. These insights inspire curiosity about what other unimaginable weather systems exist on distant worlds in our galaxy. Studying molten metal rain also provides analogs for early planetary formation, chemical differentiation, and atmospheric evolution under extreme conditions. Each storm reveals the delicate balance of energy, gravity, and chemical processes shaping alien planetary environments. The reflective metallic rivers on the night side create dazzling visual effects, showcasing the beauty and danger of extreme exoplanet weather. By studying these phenomena, scientists learn how atmospheric dynamics respond to extreme heat, wind, and chemical variability. WASP-76b serves as a model for predicting metallic precipitation on other ultra-hot gas giants orbiting close to their stars. Observations inform our understanding of exoplanet climates, enabling more accurate mapping of atmospheric layers, wind speeds, and chemical abundances. Metal precipitation provides a window into interactions between stellar radiation, planetary gravity, and atmospheric turbulence under extraordinary conditions. Studying WASP-76b offers unprecedented opportunities to understand extreme planetary environments, revealing how molten metal precipitation shapes landscapes, atmospheres, and weather in ways impossible to replicate on Earth. Future telescopes, like the James Webb Space Telescope, will provide higher resolution observations, allowing scientists to track metallic storms and chemical cycles in real time. Observing these storms will help refine models of ultra-hot Jupiter atmospheres, predicting wind patterns, temperature gradients, and precipitation behavior with greater accuracy than ever before. By studying molten metal rain, researchers can understand how heat, gravity, and chemical interactions create self-sustaining weather systems under extreme conditions. WASP-76b acts as a natural laboratory, enabling scientists to explore the limits of planetary physics, chemistry, and fluid dynamics in hostile alien environments. These insights will guide the study of other extreme exoplanets, offering clues about atmospheric evolution, chemical composition, and environmental diversity across the galaxy. Observations may reveal electromagnetic interactions between molten metal droplets and the planet's magnetic field, providing a deeper understanding of charged particle behavior in extreme atmospheres. Simulations of iron rain allow researchers to model energy transfer, condensation, and wind patterns, revealing the underlying mechanisms of alien meteorology. Future studies may uncover how metallic precipitation influences surface formation, erosion, and chemical layering, offering a new perspective on planetary geology. WASP-76b's extreme conditions challenge traditional definitions of weather, showing that precipitation can exist in forms entirely unlike Earth's water-based cycles. Understanding the planet's glowing molten rivers can inform theories about heat distribution, atmospheric circulation, and chemical transport in ultra-hot exoplanets. Researchers hope to detect similar metallic precipitation on other ultra-hot Jupiters, broadening our knowledge of extreme exoplanetary weather systems. Molten metal storms also provide clues about star-planet interactions, revealing how stellar radiation drives atmospheric chemistry and dynamic weather cycles. Studying these systems helps scientists anticipate chemical and physical processes in distant planetary atmospheres, even millions of light-years away. WASP-76b demonstrates the incredible diversity of planetary systems, reminding us that extreme conditions produce phenomena unimaginable on Earth. Insights from metallic precipitation enhance understanding of atmospheric dynamics, fluid behavior, and chemical cycles at temperatures far exceeding earthly standards. The planet's violent storms offer a model for predicting behavior of molten metals, chemical interactions, and energy transfer in other high-temperature environments. Iron rain acts as both a destructive and transformative force, continuously shaping landscapes and influencing the planet's chemical and geological evolution. Researchers can use observations to refine methods for detecting exoplanet atmospheres, interpreting spectral signatures, and estimating composition remotely. Studying ultra-hot Jupiters, like WASP-76b, prepares astronomers to identify extreme weather and chemical cycles on future discoveries. Each observation expands our knowledge of how planetary rotation, stellar radiation, and gravity drive atmospheric circulation and precipitation in alien worlds. WASP-76b challenges imagination, showing how alien physics produces self-sustaining, violent, and visually spectacular metallic storms across a constantly changing surface. By examining molten metal rain, scientists uncover processes that bridge planetary science, chemistry, and astrophysics in unprecedented ways. The planet highlights the importance of combining telescopic observation, spectroscopy, and computer simulation to understand exoplanetary phenomena fully. Each iron droplet falling from the sky illustrates the interplay of heat, gravity, wind, and chemical reaction in extreme alien weather systems. WASP-76b provides insights into how planets evolve under extreme stellar proximity, tidal locking, and intense atmospheric circulation. Observing its storms teaches us about energy transfer, condensation, and precipitation in ways impossible to replicate on Earth. The glowing rivers of molten metal create a mesmerizing, dangerous, and scientifically valuable spectacle, visible even from light years away. Understanding these processes helps prepare humanity for studying other ultra-hot planets with exotic atmospheres and extreme precipitation systems. Future research may explore how metallic storms influence planetary magnetic fields, atmospheric chemistry, and surface evolution over millions of years. WASP-76b serves as a benchmark for studying energy distribution, chemical cycling, and atmospheric dynamics.